IEEE Transactions on Haptics has a new podcast format that is designed to keep you informed about topics in haptics while you're on the go by providing a brief summary of the articles in each issue. This podcast gives an overview of the 12 articles found in the 2013 July through September issue. This issue's first article presents a new algorithm for haptic rendering of streaming range data, as opposed to the use of predefined 3D geometry. Its title is A Proxy Method for Real-Time 3DOF Haptic Rendering of Streaming Point Cloud Data by Ryden and Chiswick. The goal of this research is to develop a robust haptic rendering method that takes into consideration the discontinuous nature of point cloud data acquired by depth cameras such as the Microsoft Kinect. This paper presents a new method that extends upon the traditional approaches used in haptic rendering with the ability of using point cloud data without any preprocessing. Their method is fast enough to accommodate real-time rendering on streaming point cloud data. The authors found that their algorithm provides stable and precise rendering of the initial surface sampled into a point cloud. The significance of this work is that it enables improved operation of haptic rendering and teleoperation by including streaming data from non-contact sensors such as a depth camera. This next article is a tutorial on methods for evaluating or measuring human haptic perception. Its title is Application of Psychophysical Techniques to Haptic Research by Jones and Tan. The goal of this review is to provide guidance on how to optimally tailor a psychophysical method and experimental design to answer various research questions. This paper reviews classical and modern psychophysical techniques for measuring haptic sensory thresholds and for exploring the relationship between physical stimuli and perceived haptic sensations. The authors explain experimental design considerations that are specific to the haptic modality and highlight the factors that may bias the responses of participants. The significance of this work is in providing an understanding of how the method selected to study human perception may influence the results obtained. The review highlights the factors that may bias user judgment and the limitations of various psychophysical methods. This next article investigates the perception of an object's shape from position and curvature information through haptic exploration. Its title is Bimanual Integration of Position and Curvature in Haptic Perception by Pandey et al. The goal of this research is to understand how haptic position and curvature information are integrated in unimanual and bimanual exploration of curved objects that are too large to be completely enveloped with two hands. The authors conducted 3 psychophysical experiments to answer this question. The authors' first experiment asked participants to judge whether an elliptical cylinder was elongated horizontally relative to the radius of a cylinder estimated at the hand contact, and the performance was compared when using one or both hands. 2 follow-up experiments evaluated whether the better bimanual performance could be explained by the integration of position between the hands or the uncertainty in the location of the object center. The authors conclude that bimanual exploration of curved objects is more accurate than unimanual exploration, and that this difference is due to the integration of curvature between the hands. The main contribution of this paper is a new result that increases our fundamental knowledge of haptic shape perception and bimanual integration. This next article provides an analysis of grasping for common tasks. Its title is Grasp Frequency and Usage in Daily Household and Machine Shop Tasks by Bullock et al. The goal of the presented research is to better understand the grasping functionality of the human hand through analyzing which grasps are used the most and their important characteristics. A head-mounted camera system was used to record natural grasping motions during work from housekeeper and machinist subjects. This video data was then tagged for grasps and objects observed by trained raters, and then analyzed to determine the characteristics of the most frequently used grasps. This work is significant because there is so little real-world grasping and manipulation data available. Most manipulation data is acquired in a controlled laboratory setting. Their study provides an analysis of about 30 hours of grasping data from 4 subjects, and discusses the common grasps used, grasp durations, grasp transitions, and some common objects associated with each grasp type. This next article investigates force discrimination sensitivity of different joints during arm movement. Its title is Human Force Discrimination During Active Arm Motion for Force Feedback Design by Faizabadi et al. The goal of this research is to evaluate the sensitivity of wrist, elbow, and shoulder joints in force discrimination during movement for choosing force feedback magnitude and actuators in an active teleoperation exoskeleton. This paper presents a psychophysical evaluation of force discrimination at 4 levels of reference force using a commercial haptic device. In each trial, participants were asked to discriminate between 2 applied forces. By reducing the difference between forces as trials progressed, the authors identified the just noticeable difference in force level for each reference level and at each joint. They found that while the minimum perceivable force was similar between all 3 joints, there was a gradient in sensitivity, with the elbow being least sensitive to changes in force, followed by the wrist and shoulder. The main contribution of this work is to identify human force discrimination abilities during movement, which could be useful for neuroscientists as well as robot designers as guidelines for choosing force feedback magnitudes, resolution, and actuation depending on the joint that will be interacted with. This next article investigates how waves traveling on the surface of the skin influence the perception of vibrotactile stimuli. Its title is Mechanical and Psychophysical Studies of Surface Wave Propagation During Vibrotactile Stimulation by Sophia and Jones. The goal of this research is to study how the propagation of vibrations from an array of pager motors impacts the ability of people to localize the vibration on various parts of the body. The approach taken in this research was to first characterize the propagation of vibrations transmitted by motors mounted on the skin. This is done by using an array of accelerometers that measure the frequency and amplitude of the vibration on the motor and at fixed distances from the motor. The author's second experiment involved measuring how well subjects could localize a point stimulation on the skin when one motor of an array of 9 motors was activated. The authors found that the location and mechanical properties of the skin influence the behavior of the pager motors. The author's psychophysical experiment indicates that the primary factor that influences localization is the site on which the array of motors is mounted. The results are significant because they provide information useful for engineers and scientists involved in the development of array-based tactile displays. This next article investigates issues that could arise with the use of directional tactile cues in a mobile interface used for applications such as navigation. Its title is Mental Rotation of Directional Tactile Stimuli by Gleason and Provancher. The goal of this research is to understand how to communicate directional information using tactile cues on a mobile handheld device. This paper presents a series of 3 experiments where users responded to directional tactile cues, while the finger receiving the cues was in a variety of different arm, hand, and finger orientations. The tactile cues consisted of a millimeter of skin displacement applied to the participant's finger pad. The studies investigated how participants interpreted directional tactile cues and how quickly they were able to respond to them. The authors found that people can successfully transform directional cues between reference frames, as would be required by a user in a handheld tactile device, and that these transformations are accomplished by mentally rotating cues between different reference frames, with larger rotations and certain hand and finger poses requiring more time to process. The contribution of this research is in providing guidelines to designers of mobile interfaces that wish to provide directional or navigational information to users. This next article presents a music player that enriches the listening experience with vibration feedback. Its title is Real-Time Dual-Band Haptic Music Player for Mobile Devices by Huan, Li, and Che. The goal of this research is to enhance the experience of music listening on mobile devices with automatically generated vibrations in two frequency bands. The authors developed an algorithm that analyzes music in real time and produces matching vibrations with a miniature dual-band actuator. The frequency content of the music is analyzed to generate bass and treble signals for the vibration actuator. A user study was carried out to evaluate the subjective performance of the haptic music player in comparison with current algorithms for single-band actuators. The results indicate that users prefer the proposed dual-band haptic music player to current single-band players and provide insights for further improvements. The main contributions of the paper are experimental findings that have implications for improved multimedia experience on mobile devices. This next article explores how humans perceive vibrations produced by mobile devices. Its title is Vibrotactile Perceived Intensity for Mobile Devices as a Function of Direction, Amplitude, and Frequency by Huang et al. The goal of this research is to create a robust model of human vibrotactile perception in order to provide guidelines for engineers and application developers. This paper examines the effects of 4 physical vibration parameters: amplitude, frequency, direction, and device weight. 2 experiments assess the influence of each parameter onto the perceptual estimation of the vibration magnitude. The results of these experiments were combined in psychophysical models that forecast the intensity of the simulation as a function of the significant variables. The authors found that the perceived intensity of vibration can be estimated by absorbed vibration power to skin and is largest in the height direction, particularly above 100 Hz. The main contribution of this work is a model of perceived strength of vibration that encompasses the effects of vibration amplitude, frequency, and direction of vibration. This next article proposes design guidelines for stable and maximally transparent discrete time teleoperation. Its title is A Passivity Criterion for Sampled Data Bilateral Teleoperation Systems by Jazayeri and Tavakkoli. The goal of this study is to derive a mathematical criterion that can guide the choice of control parameters to attain maximal transparency in stable discrete time teleoperation. The authors start with considering passivity analysis of a teleoperation system that includes the continuous time dynamics of the master and slave robots and their discrete time controllers. They derive passivity and consequently stability conditions for a position error-based teleoperation architecture and validate these conditions experimentally. They found that the stability condition imposes a lower bound on the damping of the robot, an upper bound on the sampling period, and bounds on the controller gains. In the case of PD control, the bounds on the controller gains are upper bounds. This is important because high controller gains are an important prerequisite for transparency in teleoperation and can influence successful task performance. Similarly, the lower bound on robot damping for ensuring stability is important because most haptic devices have low damping for performance reasons. This next article provides guidance for implementing transient torque feedback. Its title is Directional Torque Perception with Brief Asymmetric Net Rotation of a Flywheel by Amemiya and Gomi. The goal of this research is to understand whether people are more sensitive to sudden accelerations or decelerations of a flywheel. This paper presents a device and perception experiments for providing directional torque feedback for mobile devices. The authors apply a brief unbalanced torque, suddenly rotating then stopping a flywheel to produce a twisting sensation. This use of short-duration pulses helps avoid the gyroscopic effect encountered in conventional momentum wheel torque feedback displays. To evaluate their approach, the authors conducted a psychophysical experiment in which 11 participants judged the direction of torque felt from the device and examined the torque pulse pattern needed for participants to detect the correct direction with the developed prototype. The main contribution of this paper is to show that angular velocity profiles that include sudden accelerations from rest induced the most discernible twisting sensations. This next article investigates how different forms of vibrotactile feedback can improve the control of finger force. Its title is Effect of Dynamic Vibrotactile Feedback on the Control of Isometric Finger Force by Ahmaniemi. The goal of this research is to explore how human force control can be improved using 3 different algorithms of vibrotactile feedback that is proportional to the force applied by the user. In this paper, 3 methods of vibrotactile feedback were evaluated. 1. Continuous modulation of amplitude in proportion with applied force. 2. Continuous modulation of both amplitude and frequency in proportion with applied force. And 3. Discrete bursts of vibration indicating force change with an amplitude proportional to the applied force. These feedback algorithms were evaluated in 2 tasks: repeating a certain force level several times, or holding a force level for a specified period of time. The author found that vibrotactile feedback is helpful in the short repeated task, but not in the continuous hold task. However, he found no differences in the effectiveness of the different feedback methods. The significance of this work is in showing that adding vibrotactile feedback to visual and audio feedback can be useful in user interfaces that require short but repetitive force applications, such as key entries or interaction with a touchpad. This concludes our podcast for this issue of the IEEE Transactions on Haptics. Hope you'll tune in again for our next issue.